String theory is a theoretical framework in physics that aims to reconcile quantum mechanics and general relativity, two fundamental theories of physics that have been very successful in explaining the behavior of particles and the structure of the universe, respectively. At its core, string theory proposes that all particles in the universe are not point-like particles, as in traditional particle physics, but are actually tiny, one-dimensional objects called strings. The basic idea of string theory is that the universe is made up of tiny, vibrating strings. These strings are so small that they cannot be observed directly, but their vibrations can be detected in the form of particles. According to string theory, all particles in the universe, including electrons, quarks, and photons, are nothing but different vibrational modes of these strings. The frequency of the vibration determines the type of particle, and the way the string vibrates determines the particle's properties, such as mass and charge. One of the key features of string theory is that it requires the universe to have more than the four dimensions of space and time that we are familiar with. In addition to the three spatial dimensions, length, width, and height, and the dimension of time, string theory requires the existence of 6 or 7 extra dimensions that are curled up and hidden from our everyday experience. These extra dimensions are thought to be so small that they cannot be detected by any of our current experimental techniques, but they play a crucial role in determining the properties of the particles that we do observe. String theory has the potential to explain some of the biggest mysteries of the universe, such as the nature of dark matter and dark energy, the origin of the universe itself, and the ultimate fate of the universe. However, the theory is still very much a work in progress, and there are many challenges that must be overcome before it can be considered a complete and successful theory of everything. One of the biggest challenges facing string theory is the so-called landscape problem. String theory predicts that there are a huge number of possible universes, each with its own set of physical laws and constants. This means that the theory cannot predict which universe we actually live in, and it is not clear how to test the theory against observations in order to determine which universe is the correct one. Another challenge is the fact that string theory requires the existence of extra dimensions, which are not observed in our everyday experience. This means that the theory is currently unable to make any predictions that can be tested by experiments or observations. However, there are some proposed experiments that could potentially detect the effects of extra dimensions, such as measurements of the gravitational force at very small scales. Despite these challenges, string theory remains one of the most promising candidates for a theory of everything, and it has already led to many important insights into the nature of the universe. For example, string theory has shown that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings. It has also provided a new perspective on the nature of space and time, and has suggested that the universe may be far more complex and intricate than we ever imagined.